Hey everyone, and welcome to this explainer. I am so excited you're joining me today because we are about to go on a seriously mind-bending journey. We're going to track the evolution of fundamental physics. We'll start in the safe, predictable world of classical mechanics, and then we're diving headfirst into the bizarre, counterintuitive world of quantum reality. Think of it like humanity trying to assemble a gigantic cosmic jigsaw puzzle, where the deeper you go, the weirder the pieces get. Let's dive right in. Here's a quick roadmap for our trip today. 1. The rules of the game. 2. Unifying the fundamental forces. 3. Enter the quantum reality. 4. The subatomic particle zoo. And finally, 5. The unfinished jigsaw puzzle. All right, part 1, the rules of the game. To get started, I want you to imagine that the entire universe is this unimaginably complex chess game being played by the gods. Now, we are just observers. We don't have the rulebook. All we can do is watch the board. But, if you watch a game long enough, you eventually start catching on to a few of the rules, right? Like, okay, a pawn moves forward and knight moves in an L shape. Well, in science, those rules are what we call fundamental physics. And the scientific method? That's just our organized way of watching the board, deducing those hidden rules, and making really good guesses about how the whole game is played. But here's the catch. We can't see the whole board. So how do we actually know if our guesses are right? Well, the scientific method gives us 3 neat little tricks. First, we look at simple situations. Think of this like focusing on an isolated corner of the board with just a few pieces where we can predict exactly what's going to happen. Second, we use derived rules. Say you figure out a bishop only moves diagonally. Well, then you know it's always going to stay on the same color square. You can check that derived rule even if you blink and miss a few moves. And third, there's rough approximation. You might not know exactly why a grandmaster moves one specific pawn, but you can roughly see they're building a defense around their king. In physics, we often understand nature's overall strategy without knowing what every single little atom is doing. Moving on to part 2, unifying the fundamental forces. It's really cool to look at the historical progression of all this. Back in the day, scientists had nature boxed into these neat, separate categories. Heat over here, mechanics over there, electricity, light. But as we watched the board closer, we started doing something crucial, amalgamating them. We realized, oh wow, heat is actually just the mechanical motion of atoms jiggling around. Then came this massive breakthrough. Electricity, magnetism, and light, they aren't different things at all. They are literally just different aspects of the exact same electromagnetic field. And eventually, all the different rules of chemistry were beautifully amalgamated through the quantum mechanics of atoms. Now, before the 1920s, physicists felt pretty confident they understood the basic forces. They knew about gravity, right? It's this smooth, quiet, long-range force where everything simply attracts everything else. But gravity is actually incredibly weak. Electricity, on the other hand, is a totally different beast. It is an enormously powerful, short-range force with a major twist: likes repel and unlikes attract. And because of that twist, matter tends to perfectly balance itself out. The positives and negatives cancel each other, which brilliantly hides this massive electrical force from our everyday view. But we need to talk about just how mind-bogglingly strong this electrical force is compared to gravity. Imagine you have 2 tiny grains of sand, just a millimeter across, sitting 30 meters apart. If you somehow removed that neat balance of positive and negative charges so they didn't cancel out, the electrical force between those 2 tiny grains of sand would be 3 million tons. 3 million tons. That staggering number tells us that the ultimate basis of interaction between atoms is incredibly violent and electrical, securely hidden behind a veil of perfect balance. And this concept brilliantly illustrates one of the absolute greatest amalgamations in all of physics: the electromagnetic spectrum. See, a changing electric field creates magnetism, and together they carry waves. So whether it's the radio broadcast you listen to, the radar tracking a flight, the visible light that lets you see my face, or the X-rays at the dentist, they are all the exact same phenomenon. They are all unified by just one single number: their frequency, or how many times they oscillate per second. It is just a beautifully simple rule of the gods' chess game. Okay, hold on to your hats. Part 3. Enter the quantum reality. When we zoom way into the microscopic scale, our classical understanding just completely shatters. Out here in our everyday world, classical physics rules. Newton's laws work flawlessly, objects have definite locations, and outcomes are super predictable. But down in the quantum reality of the atom, Newton's laws are completely wrong. Space and time blend together. Definite locations go out the window, replaced by blurry probabilities and uncertainty. And that clear line we draw between waves and particles totally vanishes. Waves start acting like particles, and particles start acting like waves. The absolute cornerstone of this strange new world is the uncertainty principle. It's a fundamental rule stating that you literally cannot know both precisely where something is and exactly how fast it is moving at the same time. The tighter you pin down an object's location, the wilder and more unpredictable its momentum becomes. And believe it or not, this actually solves a massive paradox. Think about it. If negative electrons are attracted to the positive nucleus, why don't they just crash straight into it? Well, because if they did, we would know exactly where they were and they would have zero motion. The uncertainty principle absolutely forbids this. So, to follow the rule, electrons are forced to leave themselves a little breathing room. They constantly jiggle with minimum motion, which elegantly keeps the whole atom from collapsing. Embracing this totally bizarre particle wave idea led to what is arguably our greatest success in physics so far: quantum electrodynamics, or QED for short. QED gives us the fully quantum mechanically correct view of exactly how light and matter interact, and it is amazingly powerful. From this one single theory springs every known electrical, mechanical, and chemical law outside the atomic nucleus. The clack of billiard balls, the glowing red of a neon sign, the very chemistry keeping you and me alive, they are all consequences of QED. It even successfully predicted crazy things like antimatter. Which brings us to part 4, the subatomic particle zoo. So, physicists actually refer to this as the horrible condition of modern physics. Outside the nucleus, our rule guessing and amalgamating worked perfectly. But as soon as we started smashing nuclei apart to figure out what forces hold protons and neutrons together, a complete mess poured out. Instead of finding a few elegant, simple pieces, experimentalists uncovered an overwhelming, completely unconnected profusion of brand new particles. We found the missing puzzle pieces, sure, but they don't seem to fit together at all. To try and make sense of this total chaos, physicists attempted to build a new sort of periodic table for the roughly 30 new particles they found in accelerators and cosmic rays. They literally had to organize them based on a property they called strangeness. We've got particles, antiparticles, vastly different masses, and things that flash in and out of existence so fast we aren't even sure if they're real particles or just transient resonances. This whole situation is a perfect representation of just how much we still do not understand. Let's try to group these chaotic new pieces together for a second. First, we have baryons, which include our old friends, the proton and neutron, but also heavier, stranger siblings. Then we have mesons, which are heavily involved in all the messy nuclear interactions. Next up are the leptons. These are the particles that hand out loose from the nuclear drama, like the electron, its mysterious heavier cousin the muon, and the ghostly, almost undetectable neutrino. And finally, we have the zero-mass carriers of forces, the photon for light, and the theoretical graviton for gravity. It is a very crowded, very chaotic zoo in there. And that leads us to our final section, part 5, the unfinished jigsaw puzzle. Fortunately, despite there being dozens of bizarre particles, there really only seem to be 4 fundamental interactions between them. This breakdown neatly summarizes our current grasp of the rules. First, electromagnetism, the coupling of photons to charged particles. Thanks to QED, we've got that law completely figured out. Second, gravity. It's ridiculously weak, but again, the law is known. Third, the weak decays, which are responsible for things like radioactive decay. That law is only partly known. And finally, the strong interaction, that enormously powerful force holding the nucleus together. Strikingly, the detailed law for this is completely unknown. We have a massive, glaring gap in our knowledge right at the very heart of matter. And so we arrive at our final thought. The stage is set. On relativistic spacetime, the rules are undeniably quantum mechanical, but the pieces of the puzzle inside the nucleus, they remain vast and deeply confusing. We are amalgamating as fast as we possibly can, but every new discovery just reveals even deeper mysteries. It leaves us with a really profound question. Is there a finite number of pieces to this? Is there an edge to the puzzle? Will humanity ever truly uncover the final hidden rules of the God's great chess game? It's a pretty amazing thing to think about. Thank you so much for joining me in this explainer, and definitely keep your curiosity alive.